Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 27, Organic Chemistry 2. In today's lecture, we will cover the chemistry of alpha, beta, unsaturated aldehydes and ketones. Properties of alpha, beta, unsaturated aldehydes and ketones. Conjugate addition of alpha, beta, unsaturated aldehydes and ketones. 1,2 and 1,4 additions of organometallic reagents. And finally, the conjugate addition of enolate ions, Michael addition, and Robinson annulation. Conjugated unsaturated aldehydes and ketones are more stable than their unconjugated isomers. Like conjugated diene, alpha beta unsaturated aldehydes and ketones are stabilized by resonance, resulting in the delocalization of the partial positive charge on the carbonyl carbon. Carbonyl carbon carries partially positive and this oxygen carries partially negative. A resonance structure where we have here positive charge and here is negative charge. That's one resonance structure. Delocalization of the positive charge from this carbon to that one is one more resonance structure. As we mentioned before, as we increase the number of resonance structure, we increase the stability. Thus, unconjugated beta-gamma unsaturated carbonyl compounds rearrange readily to their conjugated isomer. The carbon-carbon double bond is said to move into conjugation with the carbonyl group as the following examples. If we have but3-enal in acidic or basic medium, it transfers to but2-enal, more stable because of the conjugation. Here, double bond and C double bond O are isolated. Mechanism of base-mediated isomerization of beta-gamma unsaturated carbonyl compound in basic media: deprotonation first, forming enolate, which is stabilized by resonance. The negatively charged species here move on from carbon to oxygen to this carbon, which then protonated once more to form the alpha-beta unsaturated carbonyl. So from beta-gamma to alpha-beta isomerization in basic media. In acidic media, we get the oxygen protonated first, then deprotonation takes place, enol formation, the double bond conjugated diene here, en, okay, will move on the negative charge to this carbon, which gets protonated to form this species, which deprotonate to give the alpha beta unsaturated carbonyl. 1,2 addition to alpha beta unsaturated aldehydes and ketones. If you look for the alpha beta unsaturated aldehyde and ketones, we can say we have carbonyl and we have alkene functionality. So, are these compounds undergo 1,2 addition? Yes, in some cases. For example, if we react this compound with hydrogen palladium on carbon in ethyl acetate, hydrogenation gives the saturated carbonyl compound. So it is a reduction of only C double bond C. On the other hand, using sodium borohydride ethanol at room temperature produces the allyl alcohol, double, single, and then OH. So we reduce the carbonyl functionality under this condition. Reacting this compound, alpha beta unsaturated aldehyde with bromine and carbon tetrachloride, the carbon-carbon bi-system undergoes electrophilic additions and furnish the 2,3-dibromo alkanal. The carbonyl function of the alpha beta unsaturated carbonyl compounds undergoes the usual nucleophilic addition with amines, semicarboxyles, and hydrazines to form, in this example, the oxime reaction of this compound with hydroxylamine, small amount, catalytic amount of H plus, gives oxime. Conjugate additions to alpha beta unsaturated aldehydes and ketones. Several reagents add to the conjugate bi-system in 1,4 manner, a result also called conjugate addition. In these transformations, the nucleophilic part of the reagent attaches itself to the beta carbon. The nucleophilic part attaches itself to the beta carbon here, and the electrophilic part, most commonly a proton, binds to the carbonyl oxygen, forming the enol, which tautomerize to give the ketone. Okay? 1,2 versus 1,4 additions. Let's look at the oxygen and nitrogen nucleophiles. With the oxygen-nitrogen nucleophiles, usually the 1,4 products form because they are carbonyl compounds and are more stable than the species arising from 1,2 addition, like hydrates, hemiacetals, hemiaminals. Exceptions include amine derivatives like hydroxylamine, semicarboxyde, or the hydrazine, for which the 1,2 addition eventually leads to an amine product whose precipitation out of solution drives the equilibrium. Here is the alpha beta unsaturated compound reacting it with secondary amine, 1,4 products, which seems like addition on the double bond. We mentioned that. Here, the water in basic medium, addition of water, 1,4 addition again, potassium cyanide in acidic medium, yes, 1,4 addition, nucleophile cyanide attacks on the beta carbon, followed by annulation and then tautomerization to give this compound. Organometallic reagent and the regioselectivity. Organolithium reagent reacts almost exclusively by a direct nucleophilic attack at the carbonyl carbon. It's 1,2 fashion. So methyl lithium will add, nucleophile will add bond to that carbon, and the hydrogen will be on that 1,2 addition. Reactions of Grignard reagents with alpha beta unsaturated aldehydes and ketones are not generally very useful because Grignards may give 1,2 addition, 1,4 addition, or both, depending on the structures of the reacting species and conditions. It was reported that the presence of just 5% indium-3 chloride can significantly alter the amount of 1,2 products formed in these reactions. Here, this is the alpha beta unsaturated compound with Grignard, without catalyst, 1,2 addition 62, 1,4 addition 38. In the presence of 5% indium, the 2 addition increased 82 to 18%, 1/4. You can find more information about this reaction in Tetrahedron Letter 2002, Volume 43, page 887. Organocopper reagents, Gilman reagents, react almost exclusively by nucleophilic attack at the beta carbon of ketones. It's 1,4 fashion. On the basis of current information, as we know so far, conjugate addition of the lithium cuprate to alpha beta unsaturated ketones may proceed via initial reversible copper 1 olefin lithium association, then undergo oxidative addition, followed by reductive elimination and tautomerization to give the final product. Addition of trimethylsilyl chloride accelerates the conjugate addition of copper reagents to such enone properly by activating the carbonyl group. So, reacting 3-methylcyclohex-2-ene-1-one with lithium dibutyl cuprate in tetrahydrofuran in presence of trimethylsilyl chloride at -70 degrees Celsius led to the 1,4 addition where the N-butyl group bonded to this carbon, the beta carbon, and the formation of the silyl enol, followed by hydrolysis to furnish this compound, the ketone cyclohexanone derivative. Reactions of beta-beta disubstituted enones with organocuprate are often not very successful because of the static of the C double bond C around it. In these cases, using the borotrifluoride complex in ether often obviate the problem. Possibly Lewis acid boron trifluoride further polarizes and activates the ketone via coordination. So this compound reacts with lithium dibutyl cuprate with the borotrifluoride in ether at -70, then followed by hydrolysis of the intermediate led to the formation of 1,4 addition product for 4-dimethyl-octane-2-one. Reaction of dialkyl cuprate with alpha-beta unsaturated aldehydes results in preferentially 1,2 addition in case of aldehydes, not ketones. However, in the presence of trimethylsilyl chloride, conjugate addition prevails to furnish, after hydrolysis, the resultant silyl enol ether. So you get, starting from this compound, we get 1,4 addition with the silyl enols, then hydrolysis to furnish the aldehyde, saturated aldehyde. Tandem 1,4 addition, enolate trapping. We mentioned that the first step, enone reacts with dialkyl cuprate, lithium salt, to form enolate. If you would like to trap this enolate to stable form that we can identify, we can do that by O-trapping using trimethylsilyl chloride in the presence of triethylamine to form the trimethyl enol ether, where we have here silyl trimethyl group. Or we can do that by C-trapping, where we use alkyl halide or aldehyde and that will give the vicinal dialkylated product. Stereochemistry or 1,4 addition. If you are talking about the enolate intermediate, this means that we have this structure, okay, stereochemistry structure. And in this case, as we can see the butyl in one face, the attack will be from the other face of the enol, okay, and that will give predominant trans product over the cis. Okay, that's the metal group down and the CH3 up, or one in front and one in the back. Robinson annulation. Michael addition of a ketone enolate or its enamine to alpha beta unsaturated ketones gives delta diketone. If the conjugate addition takes place under strong basic or acidic conditions, the reaction undergoes a spontaneous intramolecular aldol condensation, usually with dehydration, to give a new six-membered ring, a conjugated cyclohexene on. So the first step is deprotonation, forming of enolate, 1,4 addition of enolate, the alpha beta unsaturated carbonyl, followed by protonation to give the delta di ketone, alpha, beta, gamma, and delta diketones. In basic media, again, deprotonation, enolization, followed by nucleophilic attack on the other carbonyl, followed by protonation to form this species, which will undergo E1CB mechanism pathway. Its base will attack on the hydrogen, forming the enolate, and then followed by losing OH, so it will be water molecule loss to form this cyclic hexene on. Predict the products of the following reactions: cyclopentanone, bromine in acetic acid, cyclohexanone with bromine acetic acid will give the alpha bromo. 1-phenyl ethanol plus excess iodine in base, phenyl ethanol will oxidize first by iodine as oxidizing agent to give acetophenone. This carbon has 3 hydrogen, which will replaced by the iodine, forming iodoform in basic condition, yellow precipitate, and of course plus benzoate. This compound with lithium diisopropylamide followed by propyl bromide. Here we have alpha with lithium diisopropylamide. This will be negative, then attacks on this carbon, getting this out, so this will be the product. Cyclopentanone plus benzaldehyde. Here we have carbonyl and we have alpha hydrogen. In basic medium, this will be negative, and of course supplies via resonance, enolate negative charge on oxygen. And this carbonyl, of course, but there is no alpha hydrogen, So this negative charge will attack here, followed by dehydration later on, and forming this compound as a product. Many of the condensation we have studied so far are reversible. The reverse reaction are often given the prefix retro, the Latin word meaning backward, going the reaction backward. Propose a mechanism for the to account for the following reactions. We start with this one. In basic medium, we get the starting material. Well, the first step is deprotonation, forming these species which stabilize by resonance. Then this negative charge will form a double bond and the enolate. The enolates gets protonated to tautomerize to give the cyclohexanone plus CH2CHCN, acrylonitrile. Treating this compound with acid provides this cyclohexene. In acidic medium, we get this oxygen protonated, that's first, then ring opening to form this ion, tautomerization followed by enolization to this structure, from this enol to that one, followed by nucleophilic attack to give this species, minus H plus H plus protonate this oxygen, elimination of water forming this carbocation, deprotonation provides the final product. See you next lecture.